The following program is from NET, the National Educational Television Network.
This 150-foot diameter metal frame radome is the largest structure of its kind in the world. It was originally designed for Arctic environments with winds up to 200 miles per hour. It's made of more than 3 miles of aluminum beams covered by 1.5 acres of thin fiberglass panels. Inside the protection of this golf ball-looking dome is a 120-foot aluminum dish, the world's most sensitive high-frequency radio antenna. It's made so accurately that no point on the quarter-acre surface varies from a perfect parabola by more than 75 thousandths of an inch, or about the thickness of a paper match. This 188-ton fully steerable antenna named Haystack is the most precise moving structure of its kind ever built by man. It floats on a thin film of oil and moves with such agility that it can make a full 180-degree about-face in less than a minute. Together with its transmitters and receivers, this antenna will make possible communication between men on Earth and space vehicles 100 million miles away. As a radar, it is capable of tracking a target, such as a small satellite 20,000 miles away, and probe the surfaces and atmospheres of planets hitherto beyond man's reach. As a radio telescope, it will substantially increase the precision with which astronomers can map radio sources in the sky. To take full advantage of this precise antenna, it's been designed to be pointed within 5 thousandths of a degree of its target. The aiming is not controlled by man, but by a large digital computer with a magnetic memory containing a complete astronomical almanac for the sun, moon, planets, and some of the radio sources in the sky. The operator at this keyboard types instructions to the computer, which in turn transmits 250 instructions per second to the control mechanism that moves the Haystack antenna. The computer also processes the incoming signals from the antenna, producing immediate data on a high-speed printer and graphical plots. The story of how this research facility was designed and built is our story today on Science Reporter. I'm John Fitch, MIT Science Reporter. Today we're on top of Haystack Hill in Tyngsboro, Massachusetts, at the site of the Microwave Research Facility operated by the MIT Lincoln Laboratory and sponsored by the U.S. Air Force. And this is Mr. Herbert Weiss, the project engineer responsible for the design and supervising the design and construction of this rather remarkable facility. Mr. Weiss, I wish you'd tell us a little bit about Haystack.
Fine. At the heart of this installation is a very large, precise, steerable antenna. And this antenna is unique in that the surface tolerance is maintained within a very small fraction of an inch as the antenna is rotated through the sky.
Let's see.
Now we will use this installation for experiments in satellite communications, for radar tracking experiments, and for radio astronomy.
Well, now how would you use it in these cases?
Well, in satellite communications, we would install a transmitter and receiver behind the antenna in a plug-in room, and the signals from this unit would be sent from this feed horn to the small secondary reflector and on to the main reflector.
And then they'd go out
into space to a satellite, or perhaps bounced off the moon and reflected from that object or sent back to a distant remote source. Now, if we use it for radar, we send pulses of energy. They go through the same path, and we can get echoes from distant objects.
How about for radio astronomy?
Well, for radio astronomy, we just install a receiver system at this point. And then as we point to the distant radio sources, we pick up signals, and we can plot the intensity and location of these sources.
Well, now, aside from the fact that this is a very large antenna, does it have any distinct features as opposed to other antennas?
Well, yes. For one, it was designed on taking full advantage of the capability of a high-speed digital computer, and we have thereby studied the detailed behavior of this under varying effects of gravity as we rotate it and under thermal conditions. And we've been able to incorporate compensation techniques. These are pendulum ballasts, and these are some other ballasts to minimize this distortion. Now, in addition, we have utilized this very thin shell which is on the reflecting surface, which is the reflecting surface, to help maintain this high rigidity. And we've done this by harnessing all of these panels together by means of cables around the back of the antenna, so that they, very much like the hoops on a barrel, keep the staves together. We can maintain this contour with these tension cables.
I see. Well, now, what is the purpose of having all this tremendous precision in the surface?
Well, with a very precise surface, you can operate at a very short wavelength. And with a short wavelength, then, the energy stays in an extremely narrow beam. For instance, when we operate at 8,000 megacycles, the energy from this antenna only spreads about 1 mile in 1,000 miles of travel. And therefore, when we send a signal toward the moon, for instance, which is 250,000 miles away, all of the energy falls within a circle about 250 miles in diameter.
See, that is a very narrow beam.
Now, in order to be able to utilize a beam this narrow, we've had to put the antenna under the control of a digital computer.
I see. And what does the computer do for you?
Well, the computer allows us to stay on a designated target and compensate for the rotation of the Earth.
Oh, I see. Well, I wonder if we could actually see the antenna now that we've gotten a picture of it.
Fine. Let's come this way. The radome is 150 feet in diameter and the shape of 9/10 of a sphere. And the aluminum beams have a random geometry so that they have a uniform effect upon signals arriving from all directions.
I wouldn't have realized that the sunlight would come right through the material. It must be very, very thin.
Yes, we have a typical panel here. And you know, this is a fiberglass panel. You can see how thin it is. And it's rather similar to the skin on a kettle drum, and it makes a similar sound in a high wind. Right. It has a coat of white reflecting paint to minimize the radiation from the sun.
Oh, so it won't get too hot inside the dome?
That's right. Now, if we go up the stairs, we can get a closer look at the antenna itself.
It's really tremendous. Somehow I don't get any feeling for how big it is until you get up close to it.
Now we have a large concrete pedestal. Support the structure, and perhaps we'd best look at the front of the antenna first. You'll note that we have a solid aluminum surface for the main reflector. This is 120 feet in diameter, and the signals arriving from a great distance impinge on this reflector. They're then directed toward a small secondary reflector, which is 9 feet in diameter.
Oh, yes.
And they go from that secondary reflector back into the receivers up at the focal point.
Oh, that large nose cone looking thing sticking out is the end of a plug-in box right in the middle of the antenna?
That is right. And by changing that box, we can go from one mode of operation to another.
Now, how do you get such a tremendous surface as this accurately aligned so that, as you say, no part of it is more than 75 thousandths of an inch off of where it's supposed to be?
Well, we have a special box with an optical tool, which is rather similar to the periscope of a submarine. And by looking through that special optical tool, we can observe the targets that are on the surface of the reflector. And there are approximately 1,800 targets on the surface, which can be carefully surveyed by this optical probe.
Well, if you're looking through that periscope and one of these appears to be not where it's supposed to be, then what can you do about it?
Well, we have a number of adjustments behind the antenna, which we can perhaps look at now.
I see every panel then can be individually adjusted, is that the idea?
Yes, every panel has a number of adjustments. We have these wedge blocks, which set the gap between the panel, and we have these tension cables, which run around the antenna itself to keep these panels close together.
See, these cables are, oh yes, I see.
Yeah, there's about 2,000 pounds of tension on each one of these cables. And then in addition to adjusting these elements, we can adjust the position of the reflector itself with respect to the backup structure by these adjustments. And then we have still a further tuning adjustment, which is on the back of the panels themselves.
Now, this backup structure appears to be very light. In fact, some of these look to be more like just hollow tubes than anything
Yes,
else.
they're all made of aluminum, and they're very lightweight members that have been stressed with a design level set by a digital computer, so that we have ended up with a very rigid, but at the same time very lightweight structure. The main backup ring, which is 60 feet in diameter, supports the outside members and also attaches the reflector to the elevation bearings.
So that the whole thing can rock back and forth.
The whole thing can rotate all the way around in azimuth and from the horizon up to the zenith in elevation.
Now, the plug-in boxes that fit into the back, could we take a look at one of them?
Yes, we have a test station down at the ground near the base of the antenna, which permits us to carry out equipment tests.
You mean that the test stand can actually be hooked up to your control room so the transmitter and receiver can actually be run?
That is right. We can test things on the ground while there's another unit at work in the antenna. As we walk over to the plug-in box, we have a good opportunity to observe the large concrete tower which is used to support the antenna. Now, this tower is pinned to the granite ledge and is made to be very rigid in order to obtain the precision that we need for pointing. This is the front of the RF box. This is the feed horn, which penetrates through the main reflector, and the transmitted signals and the received energy goes through this region.
What is this plastic covering for?
We pressurize this region in order to prevent dust and moisture from getting into the delicate electronic equipment.
I see, but it doesn't stop the radio
No,
waves.
it's transparent to the electrical waves. The box is 8 by 8 by 12 feet long, and each box is balanced to weigh exactly 7,000 pounds.
Why is that?
So each box will then have the same effect on the moving antenna system.
So if it's actually too light, would you actually put weight on it?
Yes,
then?
we actually have an arrangement for putting weight on it, and this unit down below is a sensitive scale which allows us to determine not only the weight, but the center of gravity, which is also trimmed up. Now, there are many connectors, cables, and signals that go in and out of the box, and we can see those. Some of those on the side. These are carry control signals. There are about 3,000 leads that go in and out of this box. Now, this is the rear of the box. I will notice that there is a lock on it.
Right.
And in order to, before personnel are allowed to be in the box, we must disconnect the high voltage. And I have a key, and by withdrawing this key from the transmitter control unit, I have turned off the energy.
I see.
And now I can put the key in this here, and I can open up the box. We can see on the left side the high power transmitter unit.
When you say high power, what do you mean?
This particular unit is capable of putting out 100 kilowatts of average power.
How would that compare with, radio stations that we're familiar with?
Well, this is twice the power in a normal large broadcast station.
Yet it doesn't seem so awfully big. I mean, I think of radio stations as having rather large transmitters.
Well, there's been considerable progress in the microwave art, and we run into very many unusual problems. One of them is that we must run cooling water through all of the components. Now, this is a sample of conventional waveguide.
I see you don't carry the electrical energy around in ordinary wires.
No, at microwave frequencies, we must use a ductwork of this sort. Now, although this is made of copper, because of the large amount of energy, even this low-loss copper has enough heat loss in it that we must carry the water away, the heat away.
Well, now, so much for the transmitter, but you also receive signals back if you're communicating or using this as a radar.
Yes, we have several very sensitive receivers, masers or parametric amplifiers, and we operate these at liquid helium temperatures of 4 degrees Kelvin in order so that they will contribute very little noise to the overall system.
You mentioned that a computer plays an important part in your installation.
Yes, we've gone to great lengths in order to exploit the capability of a digital computer, both for steering the antenna and also for processing the received signals. And if we go into the next room, we can look at the computer in operation. We are now entering the control room, and into this area, all the cables from the antenna system terminate.
I see.
And these racks of equipment contain the transmitter and the receiver components and the monitoring equipment. Now, in the far end of the room, we have a high-speed general-purpose digital computer. And this computer is used not only for pointing the antenna, but for monitoring the functions and for processing the received data.
I see.
This area is the control operator's console, and from this is the location which we use. The operator steers the antenna, controls all the other functions. Now, to demonstrate the ease with which we can point this antenna, perhaps you'd like to sit at the console and direct it.
What
Now,
sort of an experiment would we be doing here?
Well, we now have a receiver up in the antenna system.
I see that plug-in box that
And
we
this
saw.
plug-in box is a receiver. And now, by pointing the antenna at a distant noise source in the sky, a radio star, we can observe the energy which is coming in to the antenna system. Now, the first thing in order to operate the antenna is to get the attention of the computer. And you do this by pressing the return button.
All right.
Now, perhaps in order to read the computer data, we might want to move the feed, paper feed up.
All right.
You notice the computer asks you for a title. It wants to know what is this name of this experiment for its logbook.
Right.
So you ought to type in something which would register this set of data in the log appropriately.
What'll I call it?
Well, why not call it the Science Reporter Test Run? And now when you're through talking...
The only trouble is I can't spell.
Now that when you're through talking, the computer tells you what the present time is. And it says the time at this moment is 23:48 Greenwich Mean Time. Now the computer asks you whether this is going to be a real-time run or a simulation.
Well,
Now, since we want to point the antenna now, let's tell it it's a real-time run, and you do that by pushing the 0.
I see it says either 0 for this
0
one
or 1.
All right.
So
0.
now you push the 0. And the computer comes back and asks you whether you want to start this operation as soon as possible or at some future specified time. And since you want to start now, you choose 0. And now the computer asks you what you want to do. And it gives you the option of looking at an orbiting dipole belt, at a satellite, or the control of the antenna by elevation and azimuth knobs, looking at the sun, or at radio stars, or at planets, and etc. Now, in this case, since we want to look at a radio star, you
That's
should
number
pop
5.
number 5.
All right.
Now the computer automatically looks in its file, and it tells you which radio stars you may have, and it asks you to decide either by name of the star, or by the right ascension and declination. This is the coordinates in the sky.
What does that mean?
Well, it gives you the option, if you know the location in the sky where you want to direct the antenna, to manually turn over to that coordinate system. You can actually steer the antenna.
Well, what is right ascension and declination?
Well, we specify locations in the celestial sphere in a coordinate system which is essentially like latitude and longitude. The declination is the angle above the equatorial plane, and the right ascension is the angle with respect to the Greenwich meridian.
Oh, I see. If you put a plane right through the equator of the Earth, then the declination would be how far up it is from there?
That is correct.
And then how far around you
is
are
the,
from...
the declination. Now, in this case...
I don't know what the right ascension or declination is to any star.
All right. Well, then, therefore, you perhaps ought to ask for it by name. So you might want to push the number 1. And the computer now will tell you which radio stars it has in its file. And it indicates it has Cassiopeia, Cygnus, Taurus, Virgo, etc. And for this particular demonstration, Cassiopeia is a nice strong source. Perhaps we should use it.
All right. 0.
Now the computer will tell us what it knows about the present position of the radio source, Cassiopeia. Now it tells us what its right ascension is. It tells us what its declination is. It tells us this is the 84th day of the year. And it tells us exactly what the time is at this instant in Greenwich Mean Time. And now the antenna is off and running and going over to the designated coordinates. Now it's consulted a file catalog very similar to that that's in the Nautical Almanac. Now we see this is the designated position, and this is the antenna moving around to come to the same coordinates. This is one coordinate. There are other dials for the other
The
coordinates.
antenna is actually moving
The
around.
antenna is actually now moving around and is getting trained onto the radio star. Now, if we observe on this chart recorder, we can read out the signals that are coming into the receiver. The antenna now is moving around, and we'll shortly should see a response curve on this trace, which is proportional to the energy which is coming from the star.
But when it actually gets there, we'll just point to one location and then follow the star?
That is correct. It will point to the coordinates of the star, and it will stay at that location, compensating for the rotation of the Earth. If the antenna was kept stationary, the star would pass in and out of the beam in 18 seconds of time, just due to the fact that the Earth is rotating. And now we are on the star. We swung through it once before we settled down, and now we're on it. Now we're tracking the center of the star continuously and compensating for Earth rotation.
So this is energy that is actually coming from the star Cassiopeia A.
That's right. Now perhaps it would be a little more illustrative if we attempt to make the antenna scan back and forth through the star so we can see us go in and out of the response curve. Now in order to do that, you must give the computer some new instructions.
All right.
And the first thing you must do is to hit this button, which says you want the computer's attention. Now you've told the computer that you want to change the mode of operation, and it asks you, what do you want to do? Do you want to sign off? Do you want to change the type of run? Do you want to sequence into the next run? Or do you want to operate the printer?
What do I want to
Here
do?
now we want to change the mode. We want to stay on the star, but just change the mode.
Number 2, huh?
Fine. Now it asks us what we would like to do. And what we would like to do now is scan through the star. So we're
So
looking
this is what
for
we're going to
mode
change,
2.
huh?
We're going to change this element of the system. We're going to change the scanning program. And now it gives us a long list of options which we can change the mode of the antenna. Now all this time, while we're carrying on this discussion with the computer, it is continuously generating new information. And the antenna is carrying on with the function that was previously set up. And now we see the computer is giving us a long list of possibilities.
These different ways of scanning,
Yes,
is that what they'd be?
we have the option here of either scanning in elevation and azimuth coordinates, or scanning in right ascension and declination coordinates, or we could offset from the star and look at a different part of the sky, but offset at a given angle from the star we're
All
tracking.
right. Well, what shall we do here?
And we have a long list of things. In this case, we would like to do a right ascension scan.
So it'd be
We would
back
like
and
to
forth
go
this way.
back and forth across the star, and you'll notice that's option number 8,
RA scan, yeah.
RA scan. Now you tell the computer that's what you want. It comes back and says, how fast do you want to scan? At what rate do you want to go back and forth? And perhaps we ought to pick a number like 60 seconds. We go back and forth in a period of 1 minute.
All right.
You pick, fine.
Half arc in
Now
degrees.
it wants to know how far do you want to scan? How many degrees off? And perhaps if you picked a number like a half a degree,
How do I
be
make a half?
appropriate. And you go 0.5, and now you're through.
Scanning.
Now the antenna has this new instruction, and if we notice, instead of staying up at the top of the radio star and tracking it, we should be cycling back and forth through it. Now we're off the star, we were riding along with it. Here we come, right, signals are building up.
Oh, we
and
go
down
by it?
we go by, and then after a little while, after a period of approximately 30 more seconds, the antenna will stop and it will cycle back.
Go back through it going the other way.
And it will carry on this function until we decide to change the mode of operation. And this computer is now used to record this information in quantitative form. This is a display which is useful for observing what's going on, but the actual information that we use for scientific measurements is coded up in digital form and put into this computer memory. And that function is being carried out right now simultaneously with the pointing instructions and carrying on the dialogue with you and the machine. Now, after a run is over, we go to the high-speed printer and the computer, and we can get a whole table of information of this sort. And you'll notice this is a typical run. It happens to be on the radio star Taurus, or Cygnus in this case, and we have time, intervals of 2 seconds between each reading, and we have the coordinates, right ascension and declination, the effective signal level in 2 different radiometers, and then we also have the randomness between the previous runs. This is an averaging number which tells us about how valid the data is.
I see. So
over on the right side, we also have the ability to plot out the temperature. And as we go through the star, we see this plot. This helps the observer who's looking through a long series of data to pick out those parts of the record which are of real interest.
Now, how would you use this if you were using the system for communicating or for doing radar work?
Well, if we were operating for communications, we would have to have a box up in the antenna, which would contain not only a receiver, but also a transmitter.
Like the one we saw on the test stand,
Like the one we
perhaps?
saw, and they would be slightly offset in frequency. And we could send a signal from here up to a satellite, or up to the moon, or up to a passive device like echo, a passive reflector. And the signal then would be reflected off this object and relayed to a remote point. Then it could be sending data back to us on a slightly offset frequency.
And as a radar device?
As a radar, we use a transmitter which can be keyed on and off. It puts out a big burst of energy. This energy then propagates off to a distant target, and we can measure the time of transit between the transmitted pulse and the received pulse. And we can also tell something about the nature of the reflecting object, whether it's rough or smooth, how big it is, and so forth.
Well, thank you very much, Mr. Weiss. Today, we've been visiting the Haystack microwave research facility operated by the MIT Lincoln Laboratory. Our guest has been Mr. Herbert Weiss. I'm John Fitch, MIT science reporter.